So I will explain to you what is the case structure. So we hope that people who have come here at least have a basic knowledge of OpenFOAM. You have done at least the basic tutorials. So you will know that in OpenFOAM, there are basically three main folders: zero, constant, and system. And inside zero folder, you will have the boundary conditions for the various fields like pressure, velocity, temperature, and so on. Okay. And in the constant folder, as the name suggests, you will specify the fluid properties. If you have any FV models or options, that will be added there, and also the mesh will be located in the constant folder. So these are generally things that are constant, as the name suggests. Then in the system, you will have, if you are doing meshing, you will have the block mesh dict, then you will have the control dict, and some other files that are needed. Like say in this case, we wanted to run the simulation in parallel. So you need to have the decomposed power dict. So running the simulation in parallel is necessary if your simulation is time consuming. Basically, if the cell count is high, you cannot run it on one core, because basically your simple simulation they will run on one core, and all the systems nowadays will have at least four cores to six cores. So you can utilize the full capability of your system by using this decomposed power dict. I will see. I'll try to show that once. Then you have your FV schemes and FV solution. Okay, as the name suggests, FV schemes will have all the discretization schemes, for your various terms, and FV solution will have the solution algorithm that you're using. So basically, in CFD, what happens is your what you can say governing equation is discretized, right? So whatever are the discretization schemes that you use for them, like upwinding scheme for time, it will be maybe Euler scheme, backward scheme, Crank-Nicholson. All those things are specified in the FV schemes file. The FV solution specifies how you are going to solve the final system of equations that are generated. Okay, so the basic understanding of CFD is that once you discretize the domain, you create a system of equations, and they need to be solved by certain algorithms, and that are controlled by the FV solutions. Then your control dict controls your what you can say how you are going to run the simulation. What will be the start time, end time, time step, and if you need some other functionalities, that can be added as functions in your control dict. Now, as if you look at this folder structure, it is a little bit more complex, because in CHT what happens is you have multiple regions. So you have one region named fluid and the other region named metal. We could have renamed it as solid also. So it depends upon you, right? You can have a fluid, solid. If you have multiple solids, that is also possible. That is another case that I will demonstrate to you. So what happens is, in CHT case, in each of the folders, in each of zero, constant, and system folder, you will have two folders. Basically, in our case, you will have two folders, and depending upon the number of regions, you will have those many number of folders. So in zero, there will be two folders. Like in our case, we have one region that is fluid, so you will have a folder for fluid. Then you have another region called metal, so you will have a folder for metal. So in the fluid, you will have boundary conditions for the fields that are inside the fluid region. So for fluid, we will solve the pressure, temperature, and the velocity. So there will be boundary condition files for them. Now, metal region, there is no flow, right? And so pressure also, there's no meaning of that. So you will have only one file, that is a T file. So you'll have only boundary conditions for T. Similarly, when you're specifying constant, in that you need to specify what will be the what you can say your thermophysical properties, your momentum transport, that is your turbulence properties. All those things again are specified for fluid in the fluid folder, and for the metal in the metal folder. So properties for the metal are added in the metal folder. Properties for fluid are added in the fluid folder. Now this tri-surface is only specific to the snappy X mesh. If you did not have snappy X mesh, this tri-surface would not be there. Okay. Similarly, in your system folder, you need to have specific FV schemes, FV solution, and if you are going to decompose the domain, a decomposed power dict in both your fluid domain as well as in your metal domain. So inside this, what we say is the discretization schemes for the fluid are written in the fluid file. The discretization schemes for the metal are written for the metal files separately. So this is the basic structure of your CHT multi-region case. So let us go over the boundary conditions that are there for this specific case. Okay, so this is my template case. I'm just opening. So inside zero, as you see, there's fluid and metal. So in fluid, we have P, PRGH, T, and U. Okay. So why P and PRGH? So basically, whenever you have what you can say the effect of buoyancy or gravity, right, in flows, then the pressure due to buoyancy will be different, right? If you move along, like if there is elevation, if there is multi-phase flow due to density, the total pressure, what you can say, pressure will be different. The hydrostatic pressure will be different. If you remove that hydrostatic pressure, then you will have kind of like a one single pressure system for the domain. So, for ease of solving, generally from the complete pressure, the total pressure, the rho gh term, right, that is the hydrostatic component is subtracted, hmm, and you have the PRGH pressure. So, generally for multi-phase cases and for heat transfer solvers that have the buoyancy, or you can say that take into account the buoyancy effects, PRGH pressure is solved. Okay, so if you look at that, we will have boundary conditions in the PRGH file, right? But if you look at the P file, everything will be calculated. So pressure is calculated from PRGH. How is pressure calculated from PRGH? So once PRGH field is solved, you will have all the PRGH pressures. From that, you can calculate P by just adding the rho GH term over there. Okay, so that's why for P we will keep the boundary conditions for all the phases as calculated, right? And in PRGH we will be specifying the pressure. So as we've already discussed, there is an inlet, outlet, and then there is walls. So for every other for every other wall and inlet, we have given a fixed flux pressure. Okay. Now this will adjust the what I can say pressure gradient for the body force as well. So this specific type of boundary condition does that. It is similar to zero gradient, but it will slightly tweak the what I can say gradient to adjust for the body force terms. Then for the outlet, we are giving a fixed value of 0. Okay, so that is what this outlet is there for the boundary condition. So we have our P and PRGH files are done. Close this X mesh. Now T is your temperature file. So for temperature file, at the inlet, we are giving a fixed temperature of 300. So internal field is where we initialize. So it is like the initialization. So internal initial temperature is 300. For the fluid, I am saying keep the same temperature, that is 300. So it is the dollar sign means we are referring to the variable. The variable name is internal field name. So whatever was the value over here, take the same value over here. Okay, that is what it basically means. So fluid inlet will also have an inlet value of 300. Now for the outlet, we are giving a boundary condition called inlet outlet. Now this is again derived boundary conditions. They allow for reverse flow. So inlet outlet basically allows for reverse flow from the domain, right? Then this fluid to metal is the patch that gets created when you have fluid to metal is a patch that gets created at the interface. So if you see this interface that is there, right, between the fluid and the solid, that also for that also we need to specify the boundary condition. So that is what we are doing over here. This is the boundary condition of temperature. So basically what boundary condition we are using? We are using the compressible turbulent temperature coupled baffled mix. The name is very complex, but it is a simple thing. So what it is doing is it is maintaining the continuity of the temperature and the fluxes at the interface, because there should be temperature continuity. There cannot be discontinuity over there, right? Whenever the metal is getting heated, the same heat is going into the fluid. So the heat flux has to be continuous, the temperature has to be continuous. Like whenever you solve any heat transfer problems, right? At the interface between a solid and the convection, say like if you have a conduction and convection, then you will write minus k dt by dx is equal to h into delta t. That sort of a boundary condition. So what you're doing is you're maintaining continuity of the flux. So that is maintained as well as the temperature is maintained over here. And at the remaining walls, okay, we are giving zero gradient. These are the walls. This is the top, bottom, and front and back walls. Remember, this is not the walls of the geometry which is heated. The walls of the geometry that is heated has the name fluid to metal. So for that, so wherever you need coupling between the solid and the fluid, you use this type of a boundary condition. So this is similar to the coupled boundary condition of fluid, if I may say that. So P, R, J, T, and U are done. So this is for the boundary condition for the fluid. Similarly, for the metal, if you see, there is only T file, and in that case, metal will have only one interface. And so you see, in the fluid, the name was fluid to metal. In the metal, the name is metal to fluid. So it's the it is like a shadow patch that is created, right? So here also you need to specify the same boundary condition. Only difference is here the kappa method or the thermal conductivity will be calculated from the solid thermo, and there it would be calculated from the fluid thermo because that is on the fluid side. So this shows for how you get the thermal conductivity. So these are the boundary conditions, right? Let me go to. So I have looked at the zero folder. Now important, let's look at the constant folder. So extrude mesh features, polymesh, tri-surface, all these things get generated uh, during your meshing, right? What is important is this region properties file. So in region properties, you are kind of specifying what are the regions. So generally in CHT, there will be only one fluid region and one solid region. I shouldn't say one, but it is categorized into fluid and solid region. Now, fluid region, so we have only one fluid region and it is named fluid, right? So, Evan just demonstrated that when you do the split mesh regions, you have given the name fluid. If you don't give the name fluid, then by default it will take something like region 0 or something, right? And then you have to go and change everywhere. So, it's better that you overwrite it with fluid and write the name fluid over here. Okay, then for solid, I have only one region and its name is metal. So I'm adding metal over here. Apart from that, suppose if I have another solid zone or if I have another solid zone, I just give a space and write whatever the other name is. Okay, that also will demonstrate to you. So this is the way you are defining the different zones. So you have two regions and you're saying one is fluid and one is solid. So it will solve the equations for solid for in the metal region. It will solve the equations for fluid in the fluid region. This is the file that determines that. So this is one important file. Then in the constant, I will have a constant folder for fluid and constant folder for solid. So here important is the gravity. So whenever you so if you want to take into account buoyancy effects, then gravity must always be on. Okay, and then you need to look at the sign depending upon how you have oriented your geometry. So in our case, the gravity is in the downward y direction. So we have given minus 9.81. That is the gravitational acceleration in the y direction, in the negative y direction. Then momentum transport. Here you need to specify your turbulence parameters. Okay, so here we have kept the simulation type to laminar, so we are only doing a laminar simulation. If we want to what can I say, add turbulence, then we will switch this to RAS, and then RAS is then we will use all the what you can say, any turbulence parameter that comes under the RAS family, so that you can use like K omega or K epsilon or so on, right? Or maybe Spallet-Elmerus, all those things you can use. And then you can specify them and their coefficients in between. So right now we have kept the simulation type to laminar. Then we have the reference pressure. So we need to specify some reference pressure. We have added a reference pressure of 1E5. And then thermophysical properties. Now this is something that is important, right? So here in thermophysical properties, we specify what are the properties that are available, or what rather than available, what are the properties of the fluid that should be used and how those properties are being calculated. So first, the thermotype, right? So here HE rho thermo, what does this mean? HE rho thermo, it means that calculate what you can say, this thermo either based on, like you're either calculating the energy based on the enthalpy or the internal energy, and you are calculating the properties based on density rho. Okay, so that's what it means. So there are also other types like HE psi thermo. Okay, now if you see, I'm saying all these things, but if you need more details on this, right, it is always best to look at the documentation. So you go, I'm showing you how to search also. So thermophysical models. So you type thermophysical models, open form, right? And in the user guide, maybe V12 user guide. Let me go for V12 user guide. It is almost same. So if you see, they have mentioned what each of it means, right? So here, see here they have used HE psi thermo. That means the what you can say, the relation between temperature, pressure, and the properties, right? They are calculated based on the compressibility rather than, in our case, we have used rho thermo. So it is calculated based on the density, right? So there are multiple things over here. You can use rho thermo, fluid thermo, psi thermo, right? And then the thermo, here we are using E constant. Okay, you can because this is the, I think this is the fluid. So we are solving for the internal energy. So we are using E constant for the thermo. Yeah. So you can have either H constant, right? That means Cp and HF values are constant, right? Then what you can have is equation of state. So we are saying that my density is constant because here I am not accounting for the effects of buoyancy. If I have to account for the effect of buoyancy, I cannot give a constant density. If I have already imposed constant density, then how the density will vary, right? So equation of state can either be like ideal gas, perfect gas. So here these are with the various equations of states that are available. So generally, what you can say, something that is widely used is either Boussinesq or your ideal gas, right? So in Boussinesq approximation, what you do is basically the effect of the buoyancy change is only added for the what you can say the buoyancy term over there, and everywhere else in the complete region, the density is considered to be constant. So this kind of saves computational effort, and this is valid if your beta delta t value is far less than one, right? Generally, maybe like 1-2%. Such guidelines will be there. So you keep 1-2% is what I'm saying. So it will be like your beta delta t value should be 0.02 or maximum 0.03. Okay. Then you can go for Boussinesq approximation. So what this does is it changes the density based on the temperature, but only for the buoyancy term. And for rest of the terms, it keeps it constant, right? Then you can have in perfect gas and all those things, right? Perfect fluid, perfect gas. So perfect gas is like an ideal gas. So generally, either you use ideal gas or what you can say Boussinesq approximation. If you have fluid, then you use perfect fluid. You can give tabulated values also of density as a function of temperature and pressure if needed, right? So there are multiple things for you to explore depending upon your application. So for the time being, we have used a constant density. So we are keeping rho constant over here, right? Then species, if you have multiple composition, then you need to specify the species. Now, at present, only one model is available in species, and its name is also species. So what we do is inside the species, we specify the number of moles and the molecular weight of each component. Okay, so that is something that you need to do. So in this case, because we have only one species, only one will be there. If you have more than one, like if it is a mixture, then you will have multiple. Okay. Then under equation of state, we have given a constant density, right? Rho constant. So we are just having one rho value, and that is a constant value. If you would have used Boussinesq, then you would need to specify, where is that? You need to specify a reference density and the beta value. So those things will be included in the equation of state. Then for thermodynamics, that is we have used, I think, E constant. So we are specifying the what you can say CV value, that is specific heat at constant volume, and we are specifying the heat of fusion. So if we want to account for phase change or something, then HF value is added over there. Okay. Then the next thing is the transport properties, right? So for transport model, we have given a constant transport model. That means all my properties, transport properties. What are the transport properties? Generally, in any simulation, you have in CHT simulations, you have major two transport properties. One is your viscosity, that is nu, right? And the other is your thermal diffusivity, that is alpha. So these two properties have to be specified. But if you see, you have specified over here mu and Prandtl number. So how is your nu and your alpha calculated? So because your Prandtl number is nu by alpha and nu is mu by rho. So all these things are kind of linked. So from this mu and Prandtl number and your rho, you can calculate your what you can say nu value as well as your alpha value, that is the thermal diffusivity. So these two are critical in calculating your transport or your diffusion values. So this is how it is specified. So right now we have used the constant model, but if you see over here, there are a lot of other models that are available, right? As I told you here. Okay, here is another example. Yeah, if your properties are changing, so they have given you some examples. If properties are changing, how do you incorporate that, right? If there are mixtures. Yeah, so this for transport model, I have used the constant transport model, but you can say that your properties like viscosity, it is changing with temperature, right? Either it changes by this way, or it is changes by a polynomial relation, okay? Or you give a tabulated value, right? So all these things are possible. You can explore them. right? Then energy formulation, I'm using the sensible internal energy. Okay, so I'm using sensible internal energy for my calculation. Just remember this. Okay, this is for the fluid side. Go out for my metal. I have two important things. One is, first, let us go to the thermophysical properties. So here everything else remains same, but if you see, instead of He, I have He solid thermo. So this model is will be used to compute the properties, right? Now again I have pure mixture, then constant transport, and all these things. Again, I think I have gone over it. Hmm. So here I am saying what is my molecular weight, right? Then what is the transport property? Kappa means your thermal conductivity. So here you have the unit, watt per meter Kelvin. So yeah, your HF, if there is phase change, then your CV value and your density. So all these properties are needed for calculation that you specify over here. Now, something that really struck me yesterday, I don't know if some people attended yesterday's session, was that Mr. Nikhil pointed out something really nice, is that in whenever you're doing open form, you need to know these values, right? You're manually entering those values. So you get a feel for those numbers. As engineers, we should have a feel for the numbers, whatever we are putting into, right? Whether it is the size, dimension, the heat capacity values, the density values, right? And what happens generally in Fluent is you just click and then, okay, somebody asks you, okay, what is the thermal conductivity of SS? You will be, okay, I don't know. So this is actually one good point of open form, is that when you are manually entering the values, you get a feel for it. Obviously, some people will just randomly do it, but as good engineers, I suggest that you get a feel for those numbers. So what is happening? What value am I putting? So this is something that came to my mind. So I thought I will say that. The other thing is FV models. So right now, if you see the so my problem at hand was that the core is having a what you can say, core loss of 100 watts. That means whenever the transformer is working, due to the eddy current, some heat is getting generated, and that quantity is around 100 watts. Okay. Yeah. So this 100 watts of heat in the simulation, we need to add into the domain. So how do we add that? So, okay, so to add that, we are incorporating a FV models. So this FV models is a utility that OpenFOAM provides to add what you can say, some source terms for us. So in the we have named our heat source as metal heat source, and we have a type of FV model like heat source that is available. So what it does is we have said selection mode all. That means in all the cells of what this FE model file is available in the metal. So it will take all the cells within metal and add a what you can say uh, heat transfer rate of 100 watts in it, right? So if I write over here capital Q and 100, it will take the absolute value. So within the complete cells, I need to add absolute value of 100. Okay. Then the other option is I can give what you can say volumetric rate. So that means if I know the volumetric rate rather than the absolute value, then I can specify that. So it depends upon what input value you have. By the value per unit volume, like sometimes you will have volumetric heat generation rate, right? So if that is the input that is given to you, that means the heat generated per unit volume, then you can replace this capital Q by small q, and that is nothing but the heat that is generated divided by the volume of the domain. So these two types of entries are allowed over here. Okay. So we have looked at the FE models, we have looked at thermophysical properties for the metal. Okay. So now I think we have looked at all the files for the constant directory. Now let me go out and let me look at the system directory. That inside system, then what we have is we have the block mesh dict. Okay. I think this Evan explained to you briefly. Block mesh dict. What he did not explain is the decomposed power dict. I will go over that. I think, but then the decomposed power dict. Yeah, this is one, and inside fluid. So generally for CHT case, you need to have a what you can say your decomposed power dict inside your fluid as well as inside your solid domain. Okay, but as a placeholder, you also need to have it outside in the system folder. So if you see, there is also a decomposed power dict, FV schemes, and FV solution. Though these schemes and solutions are only there, but the schemes and solutions means they are part of the file structure. They are needed over there, but whatever decomposition, whatever schemes and solutions we are giving, they will be read from the separate files. Like for the fluid, it will be read from the fluid section. For the solid, or it will be read from the solid section. Okay. Now let me just open one decompose predict. So in decompose predict, you have here you specify the number of subdomains. So basically, this is the number of processors that you have, right? So how do you decide this, right? For beginners, you don't know how many subdomains you have, right? So what you generally do is you open your terminal, right? And if you are on Linux, if you're on Linux, type ls cpu, right? When you do ls cpu, it will give you all the details of your CPU, right? If I zoom, if I go up, so it is telling me that I have 2 threads per core and I have 12 cores and one socket. Uh, what is this socket? So some motherboards there may be 2 sockets, and on those 2 sockets there are 2 processors. So if there are 2 sockets, that means there may be 2 processors on your thing, and then you kind of need to multiply these, right, to get the number of what you can say cores. So here I am saying I have 12 cores per socket and I have 2 threads per core, right? So and I have only one socket. So if I multiply these three numbers, how many CPUs I will have? So I will have 24 CPUs, and that is what is written over here. Okay. So I in my simulation can specify a value up to 24. So that is the general idea over here. So I can go up to 24. But remember, just randomly increasing the number of subdomains will not help you. Okay. So you need to have a balance between because what happens is if you are increasing the number of subdomains, right, you every subdomain will need to communicate with each other, right, later on. Okay. So and if in each subdomain there are only few cells, then that kind of takes over from the advantage of having multiple cores. So you need to balance. So the by that what I mean is that the gain in what you can say speed or the reduction in computational cost is not linear with the increase in the number of subdomains. So you maybe you need to try that for your separate case, right? So here I am having 4 subdomains, and the method that I'm using is hierarchical. Okay, that means in my X, Y, and Z direction, how I need to break the blocks. So I need to break it in 2 in my X direction, 2 in my Y direction, and 1 along the Z direction, right? So that is something that you can try. Instead of hierarchical, you can also maybe write simple. Then there is Scotch. In Scotch, it takes it by itself. You don't need to specify any of these components. So if you want to know what are the various other models that are available in any of these cases, what you generally do is, suppose I want to know what are the methods that are available inside this, right? Other than hierarchical. So I can just replace this hierarchical by maybe say a word like banana, right? And then I comment this out. Now, if I run this, OpenFOAM will throw an error, right? And it will say that the keyword banana is, okay, let me just show you that. Yeah, so if you see the case is already decomposed. So if I want to demonstrate that, first I will need to delete this. Yeah, so I made change over here. Or maybe I did not save it. That was the problem. Okay, so now you understood where we make mistakes. I had not saved that file. So I need to decompose, and then because my mesh is split, so I need to use decompose per dash all regions. Okay. So you see, it threw an error, right? So it is saying decomposition method banana is not valid, and the valid ones are hierarchical, manual, matrix, multi-level, none, squash, simple, structured, right? So many are there. So you can search, each one of them, read about them, which one works in which scenario. So these are the things that you can try. Okay. So yeah, so somebody is asking, is it wise to use hyper-threading in CFD physical core is working? Yes, you pointed out rightly. You pointed that out. Uh, I think I forgot to mention that for some reason. So what Ajay is saying is really valid. So what happens? maybe let me do LSCPU again. So what happens is, in processors like this AMD, also the new Intel processors, hyper-threading functionality is there. That means in every core, right, here you have two threads. So one CPU core handles two threads. So it is switching between them, right, and then doing the work. So if you want to improve the speed of your what you can say simulation, I think you should disable hyperthreading. Okay, because it is only one core that is handling the two processes, so it will not speed it up. So your hyperthreading should be disabled, and you should use only the number of cores that are there, the number of physical cores that are there. These tools are not physical cores; then they are like kind of like virtual cores. So use only the physical core number. Yeah, thanks. Thanks for pointing that out. I kind of forgot to talk about that. Yeah, so limit to 12 cores. Okay. Yeah. So I had done changes to that. Yeah, so I was saying if you need to find what are the other options that are available in place, then you can use the keyword. I'm just saying banana that because that is what the CFD community in general says, but you can write anything. If you want, you can write monkey also. It's fine. Yeah. So in Fluid, I had made that change. So I will go ahead and remove that. Okay. So I have looked at the decomposed part deck. Yes. Yes. So fluid metal. I said that we need to add the heat source. That was done. Now we are in system. Okay. In system in fluid. Let me look at FV schemes. So again, the time discretization is done using the Euler scheme, right? Then there are gradient schemes, divergence schemes, Laplacian schemes. All these things are there for you to choose. Now, again, over here, the choice of schemes, like which ones to use, right, depends upon your problem, your mesh, right? So, one very good resource, which I have also read multiple times, is Wolf Dynamics. Wolf Dynamics, and I think for meshing. So, they have a general document for selecting the controls. You can also read for meshing. So they have a lot of documents that are available, right? So you can look at the PDFs that are available over there. So they have various PDFs that are available. So in that, they give certain guidelines, right? So that is based on years of practical experience. So basically, when you have a certain level of skewness in your mesh, when your non-orthogonality is say up to a certain level, then you need to switch between schemes, and this is something that you know will not come. What you can say will not come to you in day one or day two. It will come to you only after you have done n number of simulations. You understand what each of these schemes do, like whether they are what you can say first order schemes, second order schemes. So for this, I recommend that you take some time and do that. So see Euler method. It is an explicit formulation. So whenever you use an Euler method, you will have to select your time step in such a way that it is within the stability criteria. You can the other option is you can go for backward or you can go for Crank Nicholson. Okay, so those method will allow for a little larger time step, but they may be oscillatory also. So it depends upon the problem. So these things you decide based on again your mesh and your problem settings. So this is very problem specific. So one thing will not work for all. Generally, what you do in such cases is just copy the base tutorial that was given, right? So in your tutorials, some tutorials will be given, right, for CHT. Look at them. So that will be a good starting point for you. And then modify them based on a specific problem if it is not working properly. So that is my suggestion to you. Then FV solution. So here again, for computing my row final PRGH, right? PRGH final and my what you can say. See, because I'm solving for internal energy, so I will solve for a U equation and a E equation, right? So which solver I'll be using for that? and what will be the tolerances for that, and then the algorithm that is going on. So it is solving based on the Pimple algorithm, and if you need to give any relaxation factors. So generally in transient simulations, because this is a transient simulation, it is not advisable that you relax the equations too much, and then you will lose time accuracy. Okay, so if your solution is not converging, it is best to reduce the uh, so it is always best to use a lower time step. Okay, so that is FP schemes and FP solution. Then next is in the metal folder. Again, same thing. So there will be FP schemes and FP solution. Yeah. So again, as I said, these are problem specific. So now that's it. So let me see how to run the case. Okay. So now again, if you want to run the case, there are two options, right? One is if you have done it in series or if you have done it in parallel. Right? So if you are meshing in series, then the initial what I can say commands like block mesh, surface features, then snappy x mesh dash override, and then split mesh regions with default region name as fluid. This will create the complete mesh for you. After that, you can directly run by the CHT multi-region form command. Okay, and then you can view the results in paraform. Now, only thing over here is whenever you have multiple regions, then the normal paraform does not work, and you have to use the paraform dash built-in command. So this works. So remember this. So if you're getting error after running paraform, if you're in CHT, then you should go and use the paraform dash built-in command. Okay. Now, if you are running it in parallel, then as Evan explained, that you need to first decompose it and then run, and then over here, if you see, you need to run it MPI command. So the command works by what you can say, giving the MPI command, then the number of processors. Again, this it depends upon how many processors you have. And you cannot just change over here. You have to change over here and in the decompose predict as well. Then your solver name and then hyphen parallel is the keyword that is telling it to run in parallel. Now, after the parallel run has been done, then you reconstruct the case. You can reconstruct all the regions and then you can view the results. Okay, so let me show you. So, okay, so Snappy is done on this. So I will not decompose for simplicity. Let me run CHT multi-region form. Okay, so here you see it has started to run. Okay, and it has selected various thermophysical models. It has selected where was that part in the solid? It might have selected one. Yeah, FP models. So it has selected the FP models and it is adding a heat source to all the cells within the solid region. And then it is computing the Courant numbers. So the other thing that I forgot to tell you is the control dict. Yeah. So in the control dict, I am saying start from latest time. Now this is helpful. The latest time command is helpful if you have stopped your simulation in between for some reason, right? So we keep doing that. So say if I run it till 1 second and after that I want to restart it, I don't want to start from zero again. So then this start from will be latest time. Okay. Stop at end time. And end time I'm specifying to be 10 seconds. And the delta t that I've chosen is 0.0001. That is 0.1 milliseconds. And then I'm saying write control is adjustable write time. Okay. So with this, what will happen is I will get proper files written at proper time intervals. Otherwise, I will have files written at various, any random time intervals. Okay. Then purge write is basically used, say something for, I don't know, it may not be as helpful as in transient simulation as in steady simulation. So if you're doing a steady simulation, you keep writing the data so that suppose in between your simulation stops or it crashes, you have some file that is there which you can take and use that as an initial guess. Okay. Now, in steady simulation, you don't need to write, say, all the files, say, because I don't know when my computer will stop working, right? So that is just a guess. So if you say purge write as say 2, then it will save only the last 2 files. So I am saying that right after, say, if I say right after every 1 second, so it will save the time, it will start saving after every 1 second. Now, if I am on the 8th second, it would have saved the file for the 7th and 6th but I will not have the files for 5, 4, 3, 2, and 1. That means it keeps cleaning that. The advantage is that whenever you are doing large simulations, you don't the one file, like specifically for this case, one file that whatever I write will have a size somewhere around 300 MB. Now, if I write 100 files, that will be close to 30 GB. Okay, so if I don't want to save those many files, then it is better to use purge write. The other thing is the choice between this is important, the choice between a transient solver, right? Because right now we are running it as a transient case. So choice between a transient case and a steady case depends upon what is your application. Like for example, say if you are having a heat flux that is oscillating in nature and you want to capture the response of your system, okay, then you cannot run a steady state simulation. Okay, you want to see how your system responds to a transient change, you will have to do a transient simulation. Okay, but say for case like this, the one which we are solving, even a steady state simulation is possible. We have showed you transient, it can be switched to steady state because you are only interested in what will be my temperature at once it reaches steady state. So in that case, always go for steady state, it will converge faster. Okay, but we have showed you how to run a transient case. There is another case that I will be showing you that is very interesting. Okay, so this is the choice between steady and transient. So next, write format. I would suggest keep the write format as ASCII. For some reason, it is binary over here. Okay, ASCII means we will be able to read it. Binary, it will be in zeros and ones. So if you even if you open the file, you will not be able to read it. Change it to ASCII. Then these are just write precisions. How many what you can say decimal places you want. Hmm. Then yeah, this is something very important, runtime modifiable. So see, now if I were to change anything in my control dict while the simulation is going on, and if I have this runtime modifiable true, that means it will take the updated changes and it will start working on the simulation itself. That means I can during my runtime on the go, I can change the parameters. So if I have this runtime modifiable true, now and then if I have this adjust time step, okay, set to yes, then it will limit my maximum Courant number and my maximum diffusion number. Okay? Because if you don't want it to exceed beyond certain limit for stability regions. So if your say maximum Courant number is going higher, then it will adjust your time step and lower the time step to reduce the Courant number. And if your Courant number is say too low, then it may also increase the time step. The other thing that what we have done over here is we have added something called as a function. In that function, we are monitoring the average temperature fluid metal interface. So what we are doing over here? So yeah, we are using some function objects to gather some data, right? In this, what we are doing is we are calculating the temperature at the interface. So we are saying that use the surface field value, what you can say, this utility. And in that, I want the area average. That means area average. Area average what? Area average temperature. Because the field is temperature. Okay. Then it is available in this library. Okay. Whether it is enabled or not, true. If I want to write it, yes, write for every time step. And write interval is 1. I want to log it, yes. The write field is false because I don't want to write these fields for all time step. I just want it to be written in one file. So I kept this as false. Then the region, it is working on the metal region, and my patch name is metal to fluid. So I want the temperature of metal to fluid written over here and for the T field. So this way it gets written. So you see, once you do that, a post-processing folder gets created, right? In that, because I've said it for the metal region, a metal folder, and average fluid temperature interface gets created. In that, it starts from 0 because that is, it will create a folder according to your time. So it started at 0 time, so 0 folder will be created. So if I open that, a surface field value dot that file is available. So all the contents will be written in this file. If I open this, you see the average temperatures are written over here. Okay. Now, because obviously the simulation, the time step is very small, the values are not increasing that much. Okay. But if you run it for a longer time, it will keep running. Okay. And you can plot this. So you can either plot, you can open it, plot it in Excel, or the other thing is You can open this location in your terminal and you can use foam monitor. You should use GNU plot. Yeah, so I can also I'm sourcing it and then I'm using the utility foam monitor. So it works by this way. You specify foam monitor and then the file name. The file name is surface field value dot data. So if I just start typing and press tab, it will automatically write it. So if you see, it is starting to plot. So this is one way of monitoring the solution, right? So you want to know whether your solution has reached steady state or no. Because in the case of transient, you will not know when your solution has reached a steady state. So generally, you solve this till your curve goes this way and then flattens. Okay, and as soon as it starts to flatten out, right, means it will asymptotically reach one value, right? Then you say that okay, it has reached steady state. Then you can stop the simulation. So this is one way of monitoring the whether your simulation has reached steady state or no for the transient case. Okay, I'll just close this. So the utility that we have used is foam monitor. Pushkar, Pyfoam to track residuals. Yes, you can use Pyfoam. There is another utility, built-in utility available. We can do the same thing in using. Basically, you add a residuals. There's a file named residuals, right? You add it in your control dict, and you can use that as a function. You can call it in your. Where is my control dict? Yeah. So over here in functions, you just write hashtag and then include func and then residuals. So it will calculate residuals and you can track the residuals using the foam monitor. So that is also one way of doing that. You can use PyFoam as well. Depends, like there are many things. For some reason, but in the CHT case, for us, the residuals are not working in this V9. I don't know. Previously, it was working for us 6 months back. Suddenly, what has happened? I don't know. Some update or something. I'm not able to figure it out. It is not working only in CHT case, but I have another case. I will demonstrate in that. I'm able to track the residuals. I'm able to do the other things as well. So this is running. This was what I wanted to talk about for this specific case. Okay, so see, this is taking ages to run because I have shown that this is a transient case, right? So just let me stop that. That's why we've already run it and we have kept the case that is solved. I will open that. See, I have already solved. And you see, so many files are there. After some time, we stopped writing, because it was saving too many files. And if you see one file, its size is around 250 MB. Then if you have 100 files, then gone. So you need to decide what you want, right? So transient simulation was not needed, but okay, we thought let us show how it will evolve. That was the idea. So let me open this particular case. Yeah. So as I told you, I need to first source my OpenFOAM version. Then I will have to use Parafoam built-in. Okay, otherwise it throws an error. Yes. So if you see the data is too much, takes a little bit time to load. So if I want to view the internals, I will have to first create a slice. I will click on the slice over here. Then I want the slice to be the Z normal so that I am able to view it, right? I want to color it, say, based on velocity. Okay. I will hide the plane. And if you see, go to the last time step. Yeah. So this is how the flow is taking place. You see the flow is coming from the left and going over this block. And because we have the top, bottom, and the front and back have been given as walls, so we see no slip kind of a phenomena happening. That means we are generally capturing the boundary layer that is there. And see, Evan was talking about the add layers, right? So add layers, basically you use that to add the boundary layers near an object. So whenever you need to refine that. So again, in that he told you two options are there. One is whether you specify the last cell size, or you specify the first cell size. Generally, you go for the first cell size whenever you want to control the y plus value, right? You want to do the, what you can say, yeah, turbulence modeling, and you want to use wall functions, then specifying the first cell size accurately, right, the y plus value accurately is important, so that you can fine tune and control by the first cell height. So in that case, you control the first cell height, and then from there you need to control the transition ratio to get a nice smooth mesh. So I was talking about that. Let me go to the temperature field. So if you see in the temperature field, the block has heated up. So we have ran for around 100 seconds. In that 100 seconds, the block had reached a temperature of 490 Kelvin. Okay. So there are a few things that I wanted to show you. Yeah. Let me close this. Okay. Yeah. So I have another template for another case. So let me first open this and show you what is the case at hand. Okay. So that it becomes easier for me to talk about the case. So maybe I can do this. This will be better. Yeah. So this is better. So if you look at uh, this is a case where the outer region is a fluid. We have solved this as a 2D case, right? So this case was set up by our one of our colleagues, Divesh. Okay. So he runs the channel DD Fluids. He's very famous that way. So he had set up this case. So this is again a very interesting case when we want to demonstrate the capability of CHT, because unlike the case that we showed only two regions for simplicity. Now here we have three regions. So the central region, which is heated over here, right? That region is your heater. So that heater is embedded into a metal. That means there is a metal inside a metal, and from there it is getting heated. Generally, suppose if you want to simulate, say you have a cartridge heater embedded into a block that is heating, and then that heat is diffusing into the block, and from there it is being taken up by some fluid. So this is the application that comes to my mind. Then you can do, what you can say, this sort of an approach. Or if you want to do CPU cooling, where there is a block, there is another heater. So there are maybe, there are three layers to it. So there is a block that is the CPU itself that is generating heat. On top of that, you have the, what you can say, the heat dissipator, and then on top of that you have the fluid. So such case also. But this is different in the sense that over here the heater is completely embedded into the solid. So we have three regions. So one is the region heater, then the region metal, and then the region solid. So this is something that we want to simulate. So how we have set up this case. So let us look at that. So if you see, I'll go to the template, so it will be easier for me to explain. Yeah, so we have the zero, constant, and system folders. Can you change the color map? Yeah, I can change the color map. You want me to? The preset, maybe jet or something like that. Yeah, you can change that. That is fine. Okay. So just let me close this. Let me go to the case setup once. So nine, I use tree. Yeah. So if I run the tree command, you see that inside zero, there are three folders now. Okay. The first folder is fluid, then there is a heater, and then there is a metal. Okay. Now inside fluid, there are files for the fluid. Inside heater, files for the heater. Now this was done in a previous version in 2000 in V7. So there for some reason a P file was also needed. Okay, but from the new version onwards, the P file is not needed. Only the temperature file is needed for the heater and the metal. So that means for the solid regions. Okay. Then we have a constant folder. In that we have fluid, heater, metal, again the properties. Then another important file, region properties, as I said, that defines the regions. Then again, fluid, heater, metal. In each of them, you will have the decomposed under the system folder. You will have decomposed product, FP schemes, and FP solution. Okay. Then, as I told you, to mesh, you have two options. Either you mesh it using what you can say the toposet utility, or you mesh using Snappy X Mesh. You mesh using external mesher. Here we have used the toposet deck. So I will also explain to you the toposet deck in this case. Okay, so let me go through all the files one by one. So under 0, you have fluid. So the boundary conditions are basically the same. Okay, so if you see, P will be calculated throughout, and PRGH will have fixed flux pressure for all the walls, and outlet will have a fixed value. Okay, then under temperature, again, internal field is initialized to 300. At the inlet, the air is coming at a value of 300. Outlet, inlet outlet type of boundary condition, and coupling at the fluid to metal interface. And all the remaining walls are zero grading. So these boundary conditions kind of remain the same. So I will not go over it. Now, so if you see, there are three regions, right? So now if I open constant, something important, see in the region properties file. So if you see earlier, for our case, we had fluid and we had only metal, right? So here we have fluid, metal, and heater. So there are two solid regions. Okay. So for these two solid regions, they are defined over here in the region properties dictionary. So this is how the solver knows that for the metal and for the heater, I need to solve it as a solid. Okay. So this is my constant. Then inside each of them are my thermophysical properties. So again, thermophysical properties, I am calculating everything, the same thing as I told you, right? You need to specify the density, thermal conductivity, and the CVCP values. Now, yeah, heater. This is important. In the heater, if you see, we've added FP models. Okay, and if I open that FP models, so this is something very good. So the previous file was on V7. So in V7, somehow it was much easier to write this code. I have modified it to work in V9. So if you see, in our case, right, the one which we presented before, we were adding heat at a constant rate, right? And that heat is being added throughout. Now, in this example, what we are saying is that we want to add heat for a specific time only. Okay, and after that, we will stop heating it and then see the response. And then we look at the transient response. So that's what we are doing. So we are using the type of source as semi-implicit source. Okay, we are using the selection mode all. Again, this file is located in the heater folder. So all the cells inside the heater domain will be selected. Okay, and volume mode is absolute. Okay, that means I'm adding whatever value that I add will be added to the entire domain and not on the volumetric per cell volumetric basis. So that's what it means. Okay. Basically, it means if you have the value in watts, you keep it as absolute. If you have the value in watts per meter cube, you keep it as specific. So just remember this. Now, I'm using the semi-implicit source type of a declaration. So I will have an explicit component and an implicit. Because we are explicitly specifying our value, we will add our value in the explicit. And if you see over there, I'm using the coded type of a definition. So this coded type of a definition allows us to what you can say, change the values based on the location of the mesh, based on the time. So here what we have done is change the what you can say source that we are going to add based on the time. So if you see over here, I have defined a scalar named power amplitude just for the sake of it, right? I'm saying calling it as 100 just to show you that maybe I can use that and then modify that amplitude based on the time as well. So here I am using an if-else statement. I am saying if x is less than 1, x in this case represents the current time, okay, in this formulation. So if my current time is less than 1, I am saying return magnitude of power amplitude. That means return this return value 100. That means for time less than 1, the heat that I'm adding is 100 watts. Else, that means if time is greater than 1, I'm adding 0. That means I'm heating only for 1 second. So this is one example that we have given you. You can add a sinusoidal power input over here with this mag, right? You can add a sinusoidal power input, and this mag will give you the magnitude. Something like that also you can do, and you can look at the response. So these are some suggestions which you can do. So with this, what will happen is we are adding heat only for 1 second, and then we are stopping the heat addition. Then we see how the system responds. Okay. So after I do this, I'll close this. Yeah. So this was something that I wanted to show. Yeah. The other thing was, so again over here in the control dict, I am adding a function utility to track the interface temperature between the this I'm tracking between the heater and the metal interface. Okay. How it heats up. The other thing that I wanted to actually explain is toposet dict, right? So what happens is, maybe I will run this and then explain to you. So that will be much better. Yeah, this is a template. So, okay, I have opened it. Yeah. So I will first run the block mesh utility. Okay. Once I run the block mesh utility and I will view this mesh. You see, it is a simple mesh, block mesh, right? In which I have added small, what you can say, a fine mesh. Now, this is just one region. Okay. It has not been split into multiple regions. So my aim is that in the center, I want one solid, right? And within that, I want one heater. So block mesh has just meshed it and given me n number of cells. Now, with toposet dictionary, what I can do is I can select some cells at the center, right, which correspond to the size of my domain, right? And then I call them as, say, metal and call them as heater. So this is a simpler way of generating this mesh. That means I take already the mesh that is generated by block mesh, and only certain cells that are at the center, I will, what you can say, capture, select them and rename them, okay, as what you can say, solid or metal. So now how do I do that? So that I can do by the toposet utility. For that to work, you need a toposet dict in your control in your system folder. So over here, I will kind of explain to you all whatever is done over here. Okay. So what we are doing is under actions, whatever actions need to be taken are defined over here. So we are creating a cell set. Okay. The type is cell set. Okay. So we are calling that cell set as CS, and we are creating a new cell set, and the source is box to cell. And basically what it does is we are giving a box, right, with some endpoints, and all the cells that lie within this box are being selected by this utility source info and box, and those cells are added to the cell set called CS. Okay. Now this dimension is selected such that it matches the dimensions of the heater zone that I want. Okay. So if you see over here, my heater zone is 1, 2. So heater zone is 1 centimeter by 1 centimeter. Okay. Something kind of like that. Yeah. So all the cells within that zone, I'm selecting it and I'm calling it heater. Okay. So first is I am creating a cell set out of that, right? And that cell set, I'm converting it into a cell zone. So the second action is convert the cell to a cell zone, and that cell zone is named heater. So once I do that, if I do only this much, all the cells at the center which lie within this box will be added to a new cell zone called heater. Okay. Then after that, what we are doing is we are creating another other cell set. For some reason, we are calling it BS. Okay. We shouldn't have called it BS, but okay, we have called it BS. So I'm creating a new cell set. So all the cells within this box we will select, okay, and add it to the new cell set. Now, so basically what we are doing is around the heater there are 4 regions. Okay, that means the heater is being encapsulated by the metal. So I'm selecting only the regions around that heater. So these are the 4 zones: 1, 2, 3, and 4. So all of those 4 zones, I don't know how, maybe I should sketch it, so that will be better. So basically what we have done is, so I have, say this is my metal block. I'm now only looking at the central region, okay, leaving the fluid aside. So I have one central region called heater. Okay. So initially, what I did is I selected the endpoints. So if you remember, this is OpenFOAM always deals with things in 3D. Okay. So the heater is actually something like this. Okay. It is in 3 dimensions. So whenever we are specifying the box, okay, to capture the cells, we need to specify these corner points 1 and 2. Okay, when we specify these corner points, it will consider that to be one sort of like a zone, and all the cells that lie within that zone, it will select. So that is what the first, what I can say, command did, right? Box to cell, and then that we created into a cell set, and that cell set became a heater. So the pink one is done. Now, for some reason, what we are doing is now dividing this into 4 regions, right? So say this way, I can now do that. So I will divide it into this way. So I have 4 regions like this, right? So this will be 1, 2, 3, and 4. Okay, so I can use 4 box to cells and capture this whole remaining area. Okay, so that is one approach to do that. That is how it is done over here. Now this numbering may be different, but this is the approach. You can understand that. The second approach is, which is much more simpler, is what I would have done is, rather than that, go for a box to cell, start from here and then go to the 3rd dimension, right? And select that. So it will capture all the cells within the black box. Now, once I have captured that, the disadvantage is, remember that all the cells within the black box also lie within the pink box over here. That means within the heater. So that means all the cells of metal also have the cells of heater within that. So I would have had to delete the cells of heater in that. So I would have had to capture that all the cells within the black box and delete the cells within the heater. So that is another way of what you can say, creating a cell set for the metal region. So the one which we have demonstrated is one way, and the other is that. So I think both those ways we can try. Okay. So if you see, all these 4 cell sets are for the what I can say, the region around the metal, and then all of them. So if you see the utility, if you see, after we created one cell set, which was a new cell set, the action was new for it, right? For the others, we have the action is add, and the name remains same. Okay, so we are just adding to the same cell set. So we are kind of grouping them and adding to the same cell set. And once we have added the cells for all the regions, then we create from that cell set a region called metal by using the cell zone set. Okay. Now what we are doing is, similarly, we are using the same approach, and all the cells around the metal region now. Okay, all the cells around the metal region that are in the fluid domain, because our metal is inside the fluid domain, we are selecting all of them, right? And then adding it to the cell zone fluid. Okay, so we have created another cell set. So this is a much more lengthier way of doing it. I suggest that you create one cell set that encompasses the complete domain and then subtract the cell set. Use the delete function instead of add function. So that is one easier way of doing that. I don't know that I don't have enough time to demonstrate that, but that is something that you can try. So only the action will be, I will give you a hint that once you've got the entire cell set, then you use the action delete, and then this box to cell will be the box. Like if you, from the fluid, if you want to delete the metal and heater part, so you first create a box that contains the whole domain, then use the delete function and use a box that contains the metal with the heater embedded in it. So that was the much more easier way of doing this. Okay, so we have done that. So that was topocentric. So once we have done that, so what we have done is we have done block mesh. So after we have done block mesh, we need to run the toposet utility. S is capital. So if I run toposet, if you see over here, so it is creating cell zones, right? For the cell zone that is at the center, there are 400 cells. So these 400 cells are added to heater. Okay, then for the other, right? we have 450, then another 450 are getting added to it, then another 1,000 are getting added to it, right? No, after that, 900, 100 cells were added. Okay, and so on. And then we have for cell zone set metal, we have a total size of 1,100 cells. Okay. Similarly, for fluid, all these things have been done for fluid, and we have fluid cell zone set as 38,500. So this is our domain that we have added. Okay. Now, after I've done the topo set command, remember it has created those cell zones, but it has not split the mesh based on those cell zones. So we need to run the command split mesh regions. Into cell zone and then overwrite. So this is my command. So I have split. So once I do that, if you see inside my zero fluid, then that cell 2 region will come, and inside my constant, inside fluid, I will have a polymesh folder. That means it has split the mesh. Okay. Once this has happened, now we can run the CHT case. So see, it compiled the dynamic code for adding heat, and now it is running the case. So just give it a maybe 30 seconds or a minute to run. Let me grab a glass of water till then. So see, our simulation is done. Now we can view the results. Again, to view the results, you will go to Paracoon, and then use the built-in function. Okay, I think if I click apply, because it is 2D, I don't need to add a slice. I can directly look at my temperatures. Okay, so see, to begin with, now see with time, because we saved only after 1 second, right? So after the first second, if you would have saved in between, you would have seen the metal part also getting heated, but we saved after every 1 second. So till 1 second we've added heat. So you see it to become to be red, right? And we have reached a temperature of roughly around 310. Now in the next time step, you see that it is not heating, but it is cooling. Okay. This is because we stopped heating after 1 second. So whatever heat was added, it now is cooling that region, right? And maybe we can also look at the velocity. So this is how the velocity is for this case. Now let me show you the what I can say, the interface temperature curve. Yeah, I will close this and let me open the foam monitor, post processing heater, average temperature 0. So if you see over here, what we are doing is we're capturing the interface temperature. So till 1 second, the interface temperature was rising because we were adding heat. As soon as we reached 1 second, it started to drop. Okay. So now you see, another thing that I want to point out is, I don't know if you all missed this, is that see, whenever we added this utility in my control dict, I am getting data for every time step. Okay. And I am able to see the temperature rise. But in my paraview, right from 0, I directly go to 1. Okay, I don't have anything in between. This is because I have not written the data. Okay. And why I have not written the data? Imagine if I write the data for every 0.01 second or so, it will kind of completely, what I can say, fill my hard drive. So whenever you are doing a transient simulation, right, it is very important for you to sit, right? I don't know. This was also this also came out in yesterday's talk, and this is very important. Whenever we take courses, also over here, we say that to the students, before you touch the simulation, sit with a pen and paper and write down what you need, okay, and what you're expecting. What are the results? Any theoretical analysis, whatever it needs to be done, is done. So that is the first step of CFDs. First step of CFD is not meshing. Okay, first step of CFD is to take a pen and paper and completely break down your problem on the paper itself. Okay, so then, so I know that I want to track my interface temperature, right? That is my objective. So that's why I've added this interface temperature, what you can say, algorithm to track the interface temperature, and I'm getting this plot. if I would have simulated this case and then I want to extract this data, it wouldn't have been possible because I'm saving data at only 0 and 1 second. So you see, I would have missed that detail. So this is something that is important. Okay. So another important thing, see, over here we are only monitoring the surface temperature because I told you for some reason in our CHT case, the volume added. So for some reason that those utilities are not working. But I have another case which I have run. So with that, I can demonstrate those utilities. So I have a pipe. First, I'll demonstrate what are the contents. So I am simulating a flow through a pipe. So I don't know, I think you don't need to go through all the boundary conditions, but the most important boundary condition is for the temperature. So for the walls of the pipe, I am giving a fixed flux. Okay, and that flux we give by using the fixed gradient kind of a boundary condition. So all of us, we are accustomed to giving the zero gradient boundary conditions, but at the wall now I have given a fixed gradient boundary condition. This is because if you know Fourier's law says that Q is equal to K times my temperature gradient, that is dt by dx normal to the wall, or dt by dn is what I should say, right? So if I want to capture the gradient dt by dn, then that is nothing but the Q, that is the flux that I want to give, divided by the thermal conductivity of the medium, in this case the fluid. So that we have calculated. So my flux is 20 watt per meter square and my thermal conductivity is 0.024. So from that, my gradient comes out to be 826.45. So this is one way of adding a flux, that you give a fixed gradient. Okay. Then at inlet, my temperature is 300 and at the outlet, it is zero gradient. So this is the only boundary condition. So remember this. Now, along with that, so in the heat flux pipe, and remember, okay, one more thing I wanted to point out. See, there I did Q by K. But if you see the thermophysical properties, I am not explicitly specifying K over here, right? Thermal conductivity is not explicitly specified. The reason being, you are specifying Prandtl number, you are specifying mu, and you are specifying rho. So if you specify K, you are kind of over-defining the problem. Right, because Prandtl number is nu by alpha, alpha is K by rho Cp. So only one unknown remains, that is K, which you can get from this. So that's why the solver does not need you to specify K. If you specify, then you are kind of like over constraining the problem. So that's why K is not needed. K gets computed from these values. So it is a basic simple math. I think if you have done a little bit of heat transfer, you'll be able to understand that. So that's why we don't explicitly specify the thermal conductivity. Yeah. The next thing that I wanted to show you was my system folder. Okay, why? So in the system folder, if you look at the control dict, right, we are adding something called as volume field values. So this function works by giving you the volume averaged value of any quantity that you want. So whenever you are running a simulation and you want to know if your simulation is converging or no, like in the first case, we only were able to somehow only capture only the interface temperature, because for some reason with CHT, the volume averaging was not working. Okay. This is not CHT. This is buoyant simple form. Okay. And over here, I am able to use the volume field function and extract the average temperature inside the complete region, and I'm able to plot this. Okay, so so with this, if I do this and if I plot it, I will get the temperature. What you can say, how it is increasing. So this is something that you can add. Okay, outlet zero gradient. Somebody asked outlet zero gradient. Is it for pressure or temperature? Outlet zero gradient is for temperature. For the pressure, I have specified a fixed value, and the inlet is zero gradient in that case. So I have given a velocity inlet and a pressure outlet, so to say. Like I have specified velocity at the inlet, and at the outlet I have specified a fixed pressure of 0. Okay, so okay, yeah. So in the template we have 3 files. Similarly, we have for multi-phase and dynamic meshing as well. Yeah. So let me go to the result and directly present. Running buoyant simple form is pretty straightforward. You just run block mesh and then you run the buoyant simple form case. Okay. So see, another thing that I added over here, which I forgot to tell you, is that Yeah. Oh, I missed over there. So this field was there. So this was creating a problem. I have commented this. So if you see, I have added a heat flux post processing utility, right? So what is this doing? It is writing the heat flux on the patch wall for every time for me. So now, how will this be helpful for me? Okay, this will be helpful for me if I want to calculate what will be my heat transfer coefficient later on. Okay, so how do I intend to do that? I intend to do that in ParaView. Though if we do a little bit more advanced programming, we should be able to do this by writing a what you can say a small code of our own. That is not the agenda of this, but then using this small utility, we can do it easily in ParaView is what I wanted to demonstrate over here. So I told you that I have written a what you can say in the end a wall heat flux utility that will compute the heat flux at the wall and write it. Okay. So now if I run the case, this case is already ran. Maybe I'll just open it in terminal. It opens. I click apply. So if you see, if I do surface with edges, I have a nice structured mesh. I don't know. This is O-grid type of mesh, I feel. I might have made a mistake also in naming. So you see the mesh is refined near the wall where I want to capture the boundary layers and slightly coarser near the center where the gradients are very low. So wherever in the regions where you are expecting maximum gradient, your mesh should be fine. So this is the cross section, right? I can align the mesh along the x-axis. So this is how the mesh looks along the length. Okay. Now to view the insides, I'm adding a slice and I'm showing you the say velocity. And then if I play this, so this is how my velocity profile looks like. Okay. So I have a boundary layer that is forming at the walls. Now if I switch to temperature, I see that the temperature field is diffusing more because of the way that we have set it. And what you can say, it is combining and we are getting a combined, what you can say, thermal boundary layer. So now, once we have this, what I can do is, I showed this only to show the internal region. I'll delete this. What I can do is I can only look at the outlet patch and compute the heat transfer coefficient. So how I can do that? I can first filter and then take only the using the extract block utility, look at only the wall. So I click on extract block, click on wall and apply. So it is only selecting the wall for me. See, now everything else is gone. So only the wall. Now, okay, I missed one step. I'll go back, delete. So whenever you say import or you import the results into ParaView, right, what you need to do is any additional variables that you're generating, which are not directly part of your case setup, they don't get added into the fields directly. So you need to check them, say like the flux phi and the wall heat flux. So I want the wall heat flux to be used. So first I will go down, check it, and then apply. Then only it will be available for me for post-processing. Now again, go back to filter, then alphabetical extract block, and then I want only the wall to be extracted. Okay, so you see we have this. Okay, wall. Now, what I can do is I can compute. So use the calculator function. Now over here, if I want to calculate the heat transfer coefficient, so I call it HTC. My heat transfer coefficient is my flux. So fluxes will be in the scalar. So I go to the wall heat flux divided by, so Q is equal to H delta T. Q will be in the flux. So H will be Q divided by delta T. Yes, Q divided by delta T. Delta T will be the wall temperature. So again, wall temperature will be in the scalar minus the, now see, this is something important. Right? This, for a flow through pipe, you don't have one bulk temperature. Say if you had a flow over an external body, right, the free stream temperature is what you can use as a reference temperature. But flow through a pipe is a very different case. Even though I've demonstrated for this, so I have to show. So here there is no one reference bulk temperature, but the bulk temperature itself changes from inlet to outlet. If you read the theory, right? So this may not be an accurate representation, but my what you can say idea over here is just to demonstrate that something like this can be done. So because my bulk temperature is changing, I am now saying okay, leave it. I'm just giving the inlet temperature. That means I'm calculating it based on the inlet temperature. Okay. So this is, remember, this is not the correct approach. Okay. So for this particular problem, that is flow through pipe. For flow through pipe, your bulk temperature is not constant along the length of the pipe. Generally, it varies linearly from the inlet to the outlet. Okay, so now once I do that, if you see, it is coloring this based on heat transfer coefficient, and rightly so, heat transfer coefficient at the inlet will be very high. When the flow has just come in, the boundary layer will be thinnest over there, and so heat transfer coefficient is lowest and then increases. You can plot this and so on and so forth. So this is another way of doing this. From this, again, from heat transfer coefficient, you can compute Nusselt number. But again, then you cannot compare this with the analytical solution, only because can't we take T average? What do you mean by, okay, what do you mean by T average? You mean average of the patch? Okay, somebody had posted a question. I wanted to show you, I have mean temperature of the patch. Yes, so one thing is, remember, how you calculate the mean is very important. Okay, so if I just take a patch, like if I take an inlet or an outlet patch, let me demonstrate that. Okay, this is, I extracted the block. Maybe let's delete this. Okay, delete this. I will just directly from here, for simplicity, just look at the outlet patch. Okay, if I click on the outlet patch and then click apply, I am viewing only the outlet patch. I want to view only the, say, temperature over here. Okay, now if I do this, right, that means if I rescale it for the current time step, and if I look at it, this is the direction Z. Yeah, this is the right direction. So if you see, my temperature is hottest at the wall and cold at the center, right? This is my temperature. If I look at the velocity, okay, my velocity is lowest at the wall and highest at the center. Okay, so if I just average it for the patch, that means if I take an average area average of the temperature, that is not the correct representation of the mean temperature. The reason being, whenever you want to calculate the bulk mean temperature, you have to also take into account that maximum fluid is flowing from the center, right? Because the velocity is high over there, right? If you look at it in that terms, the velocity is high, so the amount of fluid that is going from the center will be more, and over here from the velocity. If I do rho A B like Q, right? The flux, the volumetric flux will be highest at the center and lowest at the wall. But if I look at the temperature, it is the other way around, right? So if I do just a patch average, it will mathematically average and give equal weightage to all the cells, and that is not an accurate representation. Whenever you want to do that, you need to apply it. You need to do something like rho A V and then into T. Okay, if you understand what I mean, you to understand this, I suggest that you read the book by Encro Pereira. They will explain how to calculate the mean temperature for such internal flows. So that is not the correct representation. Even if you take that, it will be better than the inlet temperature, obviously, but then it will not be accurate. If you want the accurate, then you have to compute that in that way. Okay, I think I hope that is clear. What I wanted to show you is to end with this is to show you where the solvers are, right? This CHT solver. So you know that your OpenFOAM is installed in the OPT folder. Okay, so inside OPT folder, now I have many versions of OpenFOAM installed, but I'm looking at OpenFOAM 9. In that, all your applications or your solvers are stored in the applications folder, and there inside solver. So there I can go to heat transfer solver and then CHT multi-region foam solver. And if you see inside CHT multi-region foam, there is a main C file, .c file. You can open that and you can see what is the algorithm, right? How it is calculating the different things, right? So very quickly, what I wanted to point out is, yeah, so it is just saying first it solves for the fluid region, then it solves for the solid region. That is how, if you look at it in the terminal also, it is going through all the fluid regions, solving for the fluid, then going through all the solid regions, solving for the solid by using the solve solid and solve fluid files, right? And solve fluid and solve solid files are available in the fluid and the solid. Okay, and inside that you have, say, you have solve fluid.h. So there it is saying what you need to solve the, what you can say, E equation, Y equation, rho equation. So you can go through this and try to understand this. So here, one more thing was the energy equation. Yeah, E equation. Yeah. So if you see in the energy equation, right, very simple, right? It is saying He thermo. So now what it is saying is that if your He name is E, then that means if you're solving for the internal energy, then you have a different equation. If you're solving for enthalpy, then there is a different equation. Okay. So the term only He means that you can switch between H and E, and very smartly they have done it over here. They allow, in one equation only they have kind of used like an if else statement. So if the question mark over there, right? So if it is H, if it is E, it will solve it in one way. If it is H, it will solve it in another way. If you want more reading on this, I suggest that you search for energy equation open form. Some very good content is available. Yeah, CFD Direct, correct. On CFD Direct, they have kind of nicely explained, because in open form we solve for the total energy equation. Now, depending upon which solver you are using, right? So you can switch between total energy or internal energy, right? So here you see whether you're solving for the E equation or for the H equation here. These are the two equations that I was talking about, E equation or the H equation. So you can switch between them and solve. Generally, for the solids, right, OpenFOAM 9 will not allow you to solve H equation. Solids only E equation. And for the fluid, you have a choice whether to solve for the, based on the enthalpy or the internal energy. So I suggest that you go over this. This is a very good read, right, for people who want to get more insights into this. So apart from this, I don't know, are there any other questions? Okay, Nitin is asking, is CHT multi-region foam equally fast as Fluent? See, I use both Fluent and Open Foam. So it is kind of a difficult question to answer. Now, fast in the sense of runtime, I suggest that Fluent may be faster in this case, because you see that it is just one solver which is highly optimized, right, for doing that. Now, CHT region, multi-region form may not be as fast, right? But what it really gives you is the capability, right? See, now I opened the source code and I showed you. Okay, if you want to change anything, right, as a researcher, tomorrow, if you want to see, previously the total energy equation was not being solved, right? So this is what this article is talking about, right? This article is talking about, so if you don't solve for the total energy equation, and if you solve only for the thermal energy equation, then you see that you are not capturing the, what you can say, expected analytical results, because you are missing out on some things. But they were able to modify this. So for some applications, suppose if something is not working, right, you can yourself modify and change this. This sort of functionality is available nowhere. So if you are thinking, you are comparing between Fluent and OpenFOAM, so you have to look at the pros and cons, okay, in that way. So maybe Fluent may be a little faster, and it will also converge it. That way it is also very robust, huh? It will give you converged results. And even if you make mistakes in the setup, then also it will give you results. That is also true, okay? So with OpenFOAM, you have to kind of like really know what you're setting. Otherwise, if you get kind of get incorrect results. So that way, I feel OpenFOAM is much less of a black box than Fluent, because with Fluent, even a beginner will click 2-3 buttons and they will get a solution. So my take is that, okay. So yeah, after doing one simulation on Fluent, you feel as if you are kind of mastered CFD. So that is the feeling that you get, right? So, but from my experience, Fluent is faster in this case. I'm not sure what it means. Is OpenFOAM an explicit base method or implicit? See, explicit and implicit formulations both exist. I think you mean is in time explicit, right? And implicit formulation both exist. So see, CHT, we were using an explicit formulation for time. That's why our time step was, we had to make it, what you can say, lower. You can also run it as steady state. You can run it implicit by using other schemes. Instead of Euler, you can go for backward. and so on. So that is something that you can explore. Again, you check for DDT schemes, more on it. Okay. Thank you, everyone.